Hello and welcome again to the lectures on state space approach to control system analysis and design. We discussed in last few videos about the controllability, and we have seen the Kalman's controllability, the algebraic controllability criterion. We have solved and seen state transfer problems. We have checked the controllability through Gilbert's and Haughton's criterion and a number of examples. So having understood controllability, now when we are going to look at observability, it will be much simpler, and most of the criteria, most of the things in observability are parallel to the controllability. We start with the definition of observability. A system described by the state equation x dot equal to atxt plus btut and the corresponding output equation yt equal to ctxt is said to be observable if and only if any initial state xt0 of the system can be determined using the finite record of output yt, and of course the measurements are supposed to be available throughout the time interval t0 to t1. So if using the records of inputs and outputs over a finite time interval, the initial state of the system can be determined, then the system is called as observable system. Otherwise not. Now this criterion applies to linear time varying systems, general case. This is the Kalman's observability criterion. It has a lot of resemblance with the controllability criterion, which I was telling in the beginning, that having understood controllability, observability is understood much easily. So here also the words any and finite, they have lot of significance. If any state cannot be determined, any initial condition cannot be determined based on the measurements of output and input, based on the records of output and input, even one, then the system will be treated as unobservable. Likewise, if the time involved is not finite, it may be large, but it should not be infinite. So if the time involved is not finite, then also the system will be treated as unobservable. So the sense of any by this, all the possible initial conditions in the state space should be determinable based upon the finite records of output and input. It is a necessity. Then only the system will be called as observable system. What we see that we have to determine the initial state. And how it has to be determined? Using the measurement of output. Input is known. So there is no question about availability of the record of input, but the availability of output for the time interval t0, t1. So this property of observability signifies a connection, a coupling between the output of the system and state of the system. Controllability was a coupling between the input of a system and state of the system. In place of input, observability is connecting the output and state of the system. So obviously it will have to be concerned with the matrices A and C. We have to be concerned with matrices A and C, and over and above that, this property is generic, like the controllability was. Any slight adjustment in the numerical values of the system matrix or the output matrix or both, any slight alteration can make an uncontrollable system controllable and a controllable system uncontrollable. It is possible. It is generic. And as I said, in case of controllability, controllability was a strict criterion. Even if one initial state was not transferable to final state, terminal state, system was uncontrollable. Similarly, observability criterion is also very strict in the sense, even if one initial state is not possible to be determined based upon the finite record of output and input, then the system will be simply treated as unobservable. Irrespective of we are able to determine so many other initial conditions. It is so strict. Now, what are the benefits of an observable system? If we have a system observable, what it means that all initial conditions, all possible initial states can be determined in the state space. And if the initial condition can be determined, then the subsequent state can also be determined. So observability is a form of guarantee that it will be possible to determine the system its states from the measurement of output and input. And that is, of course, the system which does this computation to determine is called as the observer. So if a system is observable, then any design specifications of the observer will be possible to achieve. An observer with fast response or sluggish response as per our wish can be designed. And it will be possible to determine all the states at any arbitrary time t0. If a system turns out to be unobservable, we considered a similar question in case of controllability. If a system turns out to be unobservable, then should we discard that system? This question may arise in our mind, and the answer is no, because with limited performance specifications, with some kind of compromise, some kind of limitation on performance specifications, an observer may still be designed to determine the initial values of some states, if not all states. And the system may be useful. So unobservable system is not necessarily a useless system, like an uncontrollable system should not necessarily be useless system. So is the case with unobservable system. So if we get an observable system, that is the ideal, but if we don't get the system fully observable, or if the system comes out to be unobservable, it may still be useful in some manner. Now we come to the Kalman's observability criterion, which is given for the time varying system x dot t equal to atxt plus btut, along with the corresponding output equation yt equal to ctxt. So there are n states and p outputs. The initial state xt0 at t equal to 0 is the initial state of the system, that is also given. So we are given a time varying system of order n and with p outputs and with this initial state xt0. Now this system is observable if and only if this observability Gramian defined by this is non-singular in the interval t0 to tf. Now This has a lot of resemblance to the controllability Gramian. In controllability Gramian, we had phi B. Here we had phi instead of phi transpose. Here B instead of C transpose. Here B transpose instead of C, and here phi transpose instead of phi. So this observability Gramian evaluated through this integral over the interval t0 to tf. If this Gramian is non-singular, if it has rank n, then the system is observable, and if its rank is not n, then the system will be unobservable. And the consequence of unobservability is that it will not be possible to determine the sum of the initial states or the initial state in an arbitrary sense anywhere in the state space. We cannot determine. So we have to check the rank of observability Gramian to be able to say whether the system is observable or not. And once the observability Gramian happens to be of full rank, then its inverse can be obtained, and then initial state can be determined. xt0 can be determined by pre-multiplying this integral with this inverse of the observability Gramian. And this integral is again similar to one integral which we had in case of controllability. So the Kalman's observability criterion not alone tells us about the observability of the system, but it also gives us a way of determining the initial condition of the system from the record of the output. It tells us that way. In case of linear time invariant system, this observability Gramian simplifies to this. So because phi tau t0 gets expressed in terms of e power a tau t0, tau minus t0, so this simplifies like this, and that further simplifies like this using the properties of integral with some change of variables. So it becomes simpler, but still it may be quite complex because we have to evaluate e power a transpose tau, we have to multiply with C transpose, then we have to multiply them with these, and then we have to evaluate the integral over the given interval. So though it is applicable, it may be computationally complex. So we have other criterion, which is algebraic observability criterion, similar to algebraic controllability criterion, and this criterion goes like this, that nth order linear time invariant system, it is applicable to linear time invariant system. Nth order linear time invariant system given in this form, A and B are now constant matrices if the system is linear time invariant, and the output equation is yt equal to cxt. Again, C is independent of time. So A, B, C are constant matrices, and we are particularly concerned with A and C matrix in case of algebraic observability criterion or in case of observability as a whole. So this LTI system will be observable if the rank of this observability matrix, this is called as observability matrix, is n. How it is obtained? There are p outputs in the system, so C matrix is p by n matrix. The C is of this size. So this is p rows. Next p rows is CA. Next p rows is CA square, and so on. We assemble this matrix, the p matrix. C, CA, CA square, etc. up to CA n minus 1. So this is n times So there are p times n rows and times there are n columns. C matrix has n columns, so CA also has n columns. So this matrix is Pn by n. Compared to the controllability matrix was n times Mn matrix. So there it was fewer rows, n rows and Mn columns. Here it is more rows, Pn rows and n columns. So this is also rectangular matrix like the controllability matrix, and if it has a rank n, then the system will be observable, the order of the system. If the rank of this matrix comes out to be less than n, then the system will be unobservable. Very similar to the controllability criterion which we had. Now we have Gilbert's observability criterion and Haughton's observability criterion, but before coming to that, we first see whether observability conclusion remains the same under a linear transformation or not. Because in order to apply the Gilbert's criterion, we may require transforming the system into diagonal form. So here is the statement which we are going to prove. This statement comes out to be correct. Observability of a linear system is invariant under a linear transformation. So if you do a linear transformation, similarity transformation, the observability of the transformed system and observability of the original system, they are same. This can be proved, and to prove it, we consider the original system with its output equation. Through the transformation x equal to tz, it will be transformed to the coordinates z, and the equivalent system will be z dot equal to fz plus gu. Corresponding output system is y equal to mz. So the A and C matrices were there, the system matrix A and output matrix C for the original system, and for the transformed system they are F and M. The system matrix is F, the output matrix is M, and the transformation is change of coordinates through the transformation matrix T, similarity transformation T. So we have this relation, F is T inverse AT, M is CT, and from this follows that A is TF T inverse and C is M T inverse. So F and M are expressed using this T in terms of A and C, and similarly A and C can be expressed using the transformation T and its inverse in terms of F and C. So now we can do some simple manipulations, because P, the observability matrix of the original system, is C, CA, CA square, etc. These matrices arranged as rows of C first, then rows of CA, and so on. And in that, if we substitute in place of C MT inverse and in place of A TFT inverse, then we can say that P will be expressed in terms of P bar. We can see. And similarly, taking P bar, the observability matrix of the transformed system, which will be rows of M first, then rows of MF, and so on. So in this, if we substitute in place of M, CT, and in place of F, T inverse AT, and if we do simplifications, then we will see that P is expressed as P bar is expressed as PT, and P is expressed as P bar T inverse through those manipulations. And because T is full rank matrix, it is a transformation, so the rank of P bar will be equal to rank of P, or rank of P will be equal to rank of P bar. And that proves our assertion that observability of a linear time invariant system under the linear transformation does not change, remains invariant. Controllability also remained invariant. So taking both the statements together, the controllability and observability of linear time invariant systems under any linear transformation remain unchanged, invariant. With that background, now we come to Gilbert's observability criterion. And why that was touched? Because it may not be necessary that system dynamics is available in diagonal form. We may require converting the system representation to diagonal form like this. Here we have to look, of course, we were looking at the system and the output matrix. We have to now look at the diagonalized system matrix, which is of course the eigenvalues on the diagonal and the corresponding output matrix, which is denoted by psi. And this is how the Gilbert criterion goes. The system in the diagonal form z dot equal to az plus bu with the output equation y equal to psi z is observable if and only if psi has no columns which are 0. Just see the resemblance. In case of controllability, we are looking at the beta matrix and we said that beta should not have any rows which are 0. So in a similar manner, resembling to the same, we are now telling that in order that the system be observable, the output matrix for the diagonalized system, the psi, should not have any columns which are 0. One or multiple columns should not be 0, otherwise the system will be unobservable, and the eigenvalues for which the psi has a column which is all elements of which are 0 will be treated as unobservable eigenvalue and corresponding mode as unobservable mode. So we see the proof is very simple. We have this as the system matrix, lambda 1, lambda 2, etc. on the diagonal, and this is the output matrix. So this psi 1, each of this, psi I from this is represented like this. So psi I is the column consisting of psi 1I, psi 2I, etc. up to psi pi. Now we are telling that the column should not be 0. So before that, let us see what happens if we try to get P bar using this psi matrix and this system matrix lambda. So we will get the psi matrices in the first row, and from psi 1 we will get lambda 1 into psi 1, then lambda 1 square psi 1, etc. And if any particular column of psi 1 of psi I is 0, then corresponding column also will be 0 in P bar, and the rank of P will be less than n. That is what is said. That proves the observability criterion, that if any of the columns of the output matrix corresponding to any of the eigenvalues, any of the diagonal entries is 0, then the system will be unobservable. So we give one example. Again, it is the same example which we considered for controllability. However, we are considering the output matrix to see the observability. This is the diagonal matrix with eigenvalues along the diagonal. And if we have the M non-zero entries in M, then the system is observable. So for example, for these values, for these entries in M, the system will be observable. Any other non-zero entries also, the system will be observable. However, if M is like this, one of the elements is 0. So one column. So if let us say it was a case of two outputs. So first one, let us say 1101, and other one, let us say some 0110. Now if this is the situation, if there are two outputs and there is no column which is 0, the system would be observable. However, if both entries become 0, or if there is only one output and one of that entries is 0, then the eigenvalue is unobservable, and the system will be treated as unobservable. So we have to look at the columns. Like in case of controllability, we are looking at the rows of the beta matrix. We have to look now at the columns of the output matrix, and therefrom we can assess, we can tell about the observability by inspection of the system matrix and the output matrix. We move further, its extension to the Jordan form. So again, the Jordan form can be in two ways. It can be the ones on the lower subdiagonal or ones on the upper subdiagonal, along with the eigenvalue on the main diagonal, the diagonal. And this is the ith block, ith Jordan block. So the matrix is J1, J2, etc. this way. We have seen this in one of the earlier lectures. So we are looking at one of the Jordan blocks, which is Ji, somewhere here, the Ji, and the corresponding that output matrix psi j. So if it in this form, we have to apply this criterion, that in case of once on the lower subdiagonal, we have to look at the last column of the output matrix of each Jordan block, last columns of psi j corresponding to the Jordan block j. And if it is the other one, this one, then we have to look at the first column. So in case of lower subdiagonal representation, we look at the last column of that psi matrix for that Jordan block, and in case of ones in the upper subdiagonal, we have to look at the first column of the psi matrix of the corresponding Jordan block. And we can again tell about the observability of the system by inspection. Of course, we have to transform the system to the Jordan form. So if the eigenvalue lambda j, for which the psi happens to have a 0 column at the required location, then it represents an unobservable situation, and the eigenvalue lambda j is the unobservable eigenvalue, and corresponding mode e power lambda j(t) will be unobservable. It will not reflect in the measurements. That is the meaning. Now we move to the hottest observability criterion, and in case of observability, we have to look at this matrix. Upper portion of this matrix this is n by n matrix, is lambda I, the identity matrix, lambda I minus A matrix. This will be n by n, and the lower portion of this matrix is C matrix, which is P by n. So this matrix has the size P plus n by n. And of course this is matrix corresponding to lambda I. So for each lambda I, lambda 1, lambda 2, etc., in case of the system having distinct eigenvalues, there will be n such matrices, lambda 1, lambda 2 up to lambda n for each lambda I. And we have to test the rank of these n matrices. Each matrix should have the rank n. Then the system will be observable. However, if any of them or more of them lead to this matrix having rank less than n, then the system will be unobservable, and those eigenvalues for which this deficit of rank happens, those eigenvalues are unobservable eigenvalues of the system, corresponding modes, unobservable modes of the system. So this is the Haughton's observability criteria. And all that discussions we did regarding ease of computation, that hold good for Haughton's or Gilbert's observability test. So they are simpler than the algebraic controllability test in case of LTI systems. We briefly discuss now the principle of duality, and this is the point. The system matrix means there is a given system and there is a dual system. System matrices, system input and output matrices here for the system, for the original system are A, B and C, and its dual system, the system matrix will be A transpose, the input matrix will be B transpose, and the output matrix will be, the system matrix will be A transpose, the input matrix will be C transpose, and the output matrix will be B transpose. This is called as the dual system of the given system. So this is a statement. The system input and output matrices of the dual system are respectively the transpose of the system output and input matrices of the original system. And in case of complex entries, they will be the complex conjugate transpose. Now, how it is useful? The principle of duality is useful in this way, that a system is controllable if its dual is observable. Controllability of a system conclusion is same as the observability conclusion of the dual system, and vice versa. Observability of a system information is same as the controllability of the dual system. So instead of checking the observability of system AC, A being the system matrix and C being the output matrix, we can check the controllability of A transpose C transpose. This is the usefulness of duality that comes. We come to the next thing, the observability subspace. So it may happen, all the systems need not be controllable, and it may happen that some system which is given like this, we are discussing the case of linear time invariant case, linear time invariant system. Suppose it happens that this system has the observability matrix P which has rank less than n, and rank of P is assumed to be n2, which is less than n. So it is a rank deficient observability matrix, implying that the system is unobservable. So what does it mean? It means that rows of this observability matrix, that C, then CA, all taken together up to Cn minus 1, these do not cover the entire state space. They fail to cover the state space, and they cover only a part of the state space or a subspace of the state space, which is of dimension n2. This subspace, which is spanned by this rows of C, Ca, etc., is n2. This is the dimension of the subspace, and it is less than n. So if a system is unobservable, a lower dimensional state space, a lower dimensional subspace is only possible to be, the states belonging to only that subspace can be determined from the output measurements. And this subspace, which is a part of the, which is a subspace of the state space, is called as the observability subspace. So I repeat, in terms of the observability subspace, that initial conditions belonging to the observability subspace only can be determined from the finite record of output and input. The initial conditions belonging outside the observability subspace cannot be determined from the finite record of output and input. This is the meaning of the observability subspace. So for a system to be observable, or let me use the terminology fully observable, the observability subspace should be the same as the state space of the system. It should have the same dimension, it should be the same for the observability. This I already said, that only those initial states which belong to the observability subspace can be determined. We move to the situation. So if we come across this situation when the system order is n and the observable subspace, observability subspace is of dimension n2, which is less than n. The observability matrix has rank n2 less than n. Then this system can be decomposed into two subsystems. One subsystem of order n2, which will be observable, and another system of order n minus n2, which will be unobservable. So a system which is not fully observable can be transformed by means of some transformation to a fully observable subsystem and a fully unobservable subsystem. And this is done using the transformation T like this, where this T is, mind it is T1, T2. For the, it is denoted differently here like this. So the T1 part is same as the linearly independent rows of the observability matrix. Because observability matrix has rank n2, it has n2 linear independent rows, and those rows are in T1. And T2 is arbitrarily chosen so that this entire matrix T will be a full rank. Then it can be used as a transformation, and with that transformation the transformed system will have this kind of a form, this kind of a appearance. So the states of the transformed system are in two groups. This is the observable states, this is unobservable states. This is n2 in number and this is n minus n2 in number. N2 is the rank of the observability matrix. So this part, n2 by n2 part, has the corresponding matrix C, and that will come observable. It will be fully observable. However, this part of n minus n2 into n minus n2, this will be this A bar, O bar, O bar matrix, unobservable part. It will have the corresponding C0, and that means the states ZO bar, they are the states which cannot be determined based on the finite record of the output and input. So we have decomposed the given system into this part. This state space of this is same as has the same dimension as the dimension of the observability subspace. Now, if it so happens that after that transformation we find that this part is stable, if we find that unobservable part of the decomposed system is stable, then this system is called as detectable. And in detectable system, what can be done is that only those states which belong to the observability subspace, they can be determined from the measurements of output and input. So we can design an observer considering these dynamics. And these dynamics will decay with time. So the states which are not observable can be assumed to be zero after some large time. So we can estimate in a detectable system only these states, these N2 states, and probably we will be still able to control that system using these states, measurement of these states, or observer of a smaller order. Probably we will be able to use and control the system. We will see this subsequently when we discuss the controller and observer design. Basically, that ZO part we determine based on measurement, and ZO bar part, ZO part we determine based on measurement, and ZO bar part we assume to be 0 for all t. And this can be represented back using the transformation T inverse to X, the state X equal to T inverse state Z, and that means the state X is determined, but in each state some part has been assumed to be 0, so it is a approximate solution of xt. It is not the exact which would have happened if the system was fully observable. So that is the limitation in case of detectable systems. We can only do observation of those components of the states which are observable. This already talked, the unobservable part will decay with time, so that is safe situation. Move further. Now if we combine the result of that controllable and uncontrollable decomposition and observable and unobservable decomposition, we get the full Kalman decomposition. A system which is neither fully controllable nor fully observable. The controllability matrix has rank n1 which is less than n, and the observability matrix has rank n2 which is less than n. So what is happening is that system is neither controllable nor observable. Then that system can be decomposed, can be transformed into 4 subsystems. One subsystem is both controllable as well as observable. Other subsystem is uncontrollable but it is observable. Third system is controllable but not observable. And fourth system is neither controllable nor observable. So a linear time invariant system which is not completely controllable and not completely observable is transformed, can be transformed into 4 subsystems. One completely controllable and observable, one only controllable but not observable, one not controllable but observable, and one neither controllable nor observable subsystem. This is the Kalman decomposition, and this is what the representation happens through a suitable transformation. This is the part which is both controllable and observable, and this is the part which is controllable but not observable. This is the part which is not controllable but observable. It is not controllable but observable. And this is the part which is neither controllable nor observable. So this kind of a thing is graphically represented like this. This is the input U to the system, and this is the controllable part written as C. This is the uncontrollable part, but it contributes to the output. This part is controllable, but nothing goes from this to the output. So this is CO, controllable and observable. This is uncontrollable, that is C bar, and observable, of course, it is reflecting in the output. This is controllable C, but its output is not reaching to the output of the system, and this is that part which is neither controllable nor observable. So neither the input is coming to this nor the output is going for this, and this is internally the situation. Externally the system will look like this. These things will not be apparent. The output input description, the input output description will not reflect this component, and this component. It will only reflect this CO component. So when we represent the systems by transfer functions, this can happen, that the uncontrollable and unobservable part of dynamics, they don't reflect in the system behavior. In case the system turns out to be stabilizable and observable, that will never be noticed also. However, if the uncontrollable part is not stable, or if the unobservable part here or here is not stable, so if uncontrollable and unobservable parts are not stable, then the system behavior will contain some kind of unexplained dynamics. And this decomposition helps us to see that how that unexplained dynamics can come into the system. So this is the advantage of breaking the system into that controllable, observable and other three systems, full Kalman decomposition. We summarize: the observability of dynamic systems can be determined by checking the rank of observability Gramian. This method is applicable to time varying system also. However, there is a lot of mathematical work, mathematical manipulation involved in testing the rank of observability Gramian, the determining the observability and testing its rank. So for linear time invariant systems, we have other methods like algebraic criterion, Gilbert's criterion or the Haughtus criterion. They can be used to check the controllability and observability of the system, both controllability as well as observability. The other form is, we have seen the Gilbert's criterion, which applies to the diagonal form representation. There the controllability and observability are assessed by inspection of the system, and effort involved is only to transform the given system to diagonal form. And in case of Haughtus, we have seen that happens to be even simpler compared to the Gilbert. And then we saw that the algebraic test could be numerical, susceptible to numerical ill conditioning. This point you will appreciate more if you solve some examples. So the controllability and observability test based on rank of controllability matrix and observability matrix, they are susceptible to numerical ill conditioning. However, the Gilbert's and Haughtus criterion tests are not susceptible to numerical ill conditioning. They give better results. And other advantage of this Gilbert's and Haughtus criteria are that they tell about unobservable eigenvalues, unobservable part of the dynamics and unobservable part of the dynamics, that both controllability aspect as well as the observability aspect. So this controllability and observability, these, as I said in the beginning of discussion on controllability as on observability, that if a system comes out to be controllable, then it is a guarantee that by a suitable design of controller we can achieve any desired response. Any performance specifications can be met in case of a controllable system. And similarly, in case of an observable system, any performance specification on design of observer can be met. So this controllability and observability, these considerations, they are very important. They are useful in controller design, observer design, state estimator design. We will see as we proceed in the course. Thank you very much. See you again in another lecture.